Okay, so there's two types of redox reactions, disproportionation and calm proportionation, that basically look different than your typical redox reaction. So let's take a look at the disproportionation example. So you're going to notice right off the bat what's different about it is there's only one reactant. So if we were to assign oxidation numbers here, so this is hydrogen peroxide. So hydrogen is +1 and the oxygen in peroxide is -1, right? So hydrogen is +1 in water, -2 in water, and 0 in oxygen gas. So what's happening here is the oxygen is actually doing both changes. So some oxygen atoms are being reduced by going from -1 to -2, right? They're gaining. But others are becoming oxidized. So you have oxygen going from -1 to 0. So it's the same species that is both being oxidized and reduced. So actually it's the oxidizing agent as well as the reducing agent. Calm proportionation is the opposite. So this is where you have the same product that's made. So you have, for example, we have chromium +1 and chromium +3 becoming chromium +2. So you have some chromiums that are being oxidized, right, going from +1 to +2. And you have chromium that is going from +3 to +2, so it's being reduced. So one species is reduced, the other is oxidized to form the same product. Okay, so we're going to look to see, well, how would we go about balancing some of these? Okay, so we're going to do the following one, and it's in a basic solution. Okay, so when it says perform a check on each, usually what that means is you're just looking to see if the charge is balanced. So you check the number of elements on both sides and the charges on both sides. Okay, so don't worry about that. I mean, you kind of naturally check it over that way anyways. So usually, remember how I was saying, like, it's kind of straightforward to see who goes with what, right, when you're doing your half reaction. Because with a disproportionation reaction, you have only one reactant, that reactant is going to be in both equations, right? So I'm going to have HXeO4 -1 becoming, and then I'm going to have another one. Like my two half reactions are both going to look the same on the reactant side. Now on the product side, usually you split the products, okay? You kind of have to look to see, well, what elements are involved. But to be honest, they all have xenon, oxygen, and actually just xenon and oxygen as a combination. So you can do this in a few different ways, right? So I'm going to put this guy up here and these two down here. To be honest, when it's something like this, where there's multiple, like more than just two products, so let's say this O2 was not there. Okay, then this is exactly what you would have done. You would split the products in the half reaction. So one would go with one would go with the other. Because you have a third product, it doesn't matter which reaction you give that third product to, it should actually balance properly no matter what. And I actually did try this out. So that's kind of what the suggested is, just to put it with whoever. But I tried it both ways, and it does come out to the final reaction anyways at that point, right? So if we were to add the O2 up here or the O2 down there, you're going to get the same answer regardless. If this was an element that could only go with one side, I don't think that would be. And usually the case is you have only two products. If you have multiple, more than two, let's see, is there one here? So for example, this guy, right, you would split this. This would be one half reaction, this would be the other half reaction. If there was a third thing here, you can put it with whichever. Okay, it should come out to the same answer regardless. Okay, so let's take a look. So we're going to balance these out. So now when you balance this, this is the same way. This process is exactly the same, right? So you're going to do the OOHE. So we have the same number of xenons already. So oxygens, we have 4 versus 8. So we're going to need to have 4 waters. And then we have to do our hydrogen. So we have 8 plus 1, so we have 9. 9 hydrogen ions, right? And then we have, what else do we need to do? Our charge. So we have -1, and actually on this side you have +4, sorry, -4, -4 plus 9, so you have 5. So this side's 5, this side is -1. So that means we need 6 electrons on the product side to get that to be also -1, right? So -4 plus -6 is 10, plus 9 is -1. So that works out. So because this is a basic solution, we can choose to do the hydroxides now, or we can do the hydroxides later. It's up to you. I'm actually going to choose to do it later because I find it's easier when it's after everything's been kind of cleaned up. So right now I'm just going to go through the same process with the other half reaction. So we're going to do the others first. So we have 1 xenon, 1 xenon. We have 4 oxygens. That means we need 4 H2O, right? We have 8 hydrogens versus 1. So that means we need 7 more hydrogens. And then for charge, we have negative, so we have +7 plus -1, so that's +6. So we need to have 6 electrons on this side in order to balance that out. All right, so now let's check our electrons. We have 6 electrons and 6 electrons. All right, so we don't have to multiply by an integer. So we're going to add the 2 together. So we're going to have 2 H, I'm just going to clean that up right now because we have this times 2. Plus, we have 4 waters, plus 7 hydrogens, plus 6 electrons. I gave way too much space. Arrow. Xe plus 4 waters, plus our XeO6 -1. Oh, sorry, -4. Plus O2, plus, oh God, why can't I remember this? Plus 9 hydrogens, plus 6 electrons. Okay, so let's do a little cleaner upper here. So we have 4 waters, 4 waters. We have 6 electrons, 6 electrons, 7 hydrogens, so that's going to come down to 2. So we have 2 HXeO4, arrow, Xe plus XeO6 -4 plus O2 plus 2H2. Okay, much easier to deal with. So now the last step, so like I said, you could have done your hydroxides before, but I'm going to do them now. So for every hydrogen, we need to add the same number of hydroxides to both sides. And then this would make 2 H2O. So there's nothing else to balance out here because we've already done with that. So a way to check, right, obviously you would check all of your atoms, but a quick check is just for the charges. So this side has -4, and this side also has -4. Okay, so conproportionation, this is actually a little bit easier, right? So 1/2 reaction is going to be BrO3 going to Br2. The other one is going to be Br negative going to Br2, right? So you go through the exact same process. So I'm just going to write down what the final answer would be here because I feel this is being a little bit repetitive. But essentially, you're just going to do the same thing. You do your other, you do your oxygens, your hydrogens, you do your electrons. Make sure the electrons are the same before you add the 2 together. And yeah, probably for the next 2, yeah, maybe let me show you one comproportionation, and then maybe this one I will not get into detail with. At least you can see one the other way around. Okay, so we do the other. I'm just going to do both at the same time, actually. So the other, okay, good. Oxygens, we have 6 waters. Here on this side, we're good. Here for hydrogens, we need 12 hydrogens on the left. Here, we don't have any hydrogens. Let's do a charge check. So we have +12 and -2, so +10. So that means we need 10 electrons in order to get that to be 0. Here we have -2, which means we need 2 electrons on the right to get that to be the same. Okay, so we have 10 electrons versus 2, so that means this whole thing's got to multiply by 5. So this is going to be 10, 5, 10, and then we would add that up. So we would have 2BrO3 plus 12 hydrogen plus 10 electron plus 10 BRs, making, so we have Br2 and then 5 Br2, so we have 6 Br2s, right? So we're adding that up, 6 H2O plus 10 electrons. So 10 electrons cancel, and I think that's all that can cancel. So at this point, we're going to add our hydrogens, or hydroxides, I should say. So we have 12OH plus 12OH. This will make 12 waters, which will cancel 6 of those other waters on that side. So we would have 2BrO3 plus 6 water plus 10 BRs, making 6Br2 plus 12 hydroxides. And we've got negative 12 on both sides. Yeah. And actually this guy, tricky. This guy, we should be simplifying the coefficients because we were able to. So this should really be 3, 5, 3, and 6 to be proper. Okay. So number 3, I'm not going to go through in detail because it's very similar. It's actually much more simplified than the first one. But basically, 1/2 reaction would be this, becoming CH4. The other half reaction would be the same reactant, becoming CO2. And then again, following exactly the same steps. So just so that you know to have the correct answer here, you should end up getting at the end of the day, after everything is said and done, 2 waters plus 2 CH3COO. Then this is going to be 2 CH4 plus 2 hydroxide plus 2 CO2 plus, actually that's it. And then this is another one where you can simplify. So this would actually just be 1, 1, 1, 1, 1. Okay? So if you have questions about this one, obviously please speak to me in class. We can do that. Okay. I'm going to pause this here because I want the next method to be a separate thing so you can watch it on a separate day. Normally I split this over 2 days. So we're going to pause this and then we're going to do one more section on the new different method. It's very repetitive, but it's kind of a new approach. Okay, you do need to know both ways.